This is Algebra, section 10-6, similar triangles. My name is Mr. Rupp, and in this video I will show you how to determine if two triangles are similar, and also how to find missing pieces of two similar triangles. By the end of the video, you should be able to use ratios to solve problems involving similar figures. Let's get started. Similar triangles. The word similar in our language means resembling but not identical, okay? Similar is resembling something, but it's not identical. It's not the same exactly. So when we're talking about similar triangles then, all right, we're talking about two triangles that are the same shape, but not necessarily the same size. So two triangles with the same shape, but not necessarily the same size. So how do we determine if two triangles are similar? Remember a couple of definitions first, okay? Ratio. All right, who knows what the definition of a ratio is? A ratio, remember, is a comparison of two numbers by division. All right, so 1/2 is a ratio. One's being compared to 2 by division. The next thing we need to remember is, what is a proportion? Yeah, I know, that's digging way back there. Okay, but that's not too hard. All right, a proportion is an equation stating that two ratios are equivalent. Stating that two ratios are equivalent. For example, this would be a proportion. 1/2 is equal to 2/4. That is a proportion. So there are two ways to test if two triangles are similar, okay? So we'll have similarity tests. All right, so test number 1 says that if the angles of one triangle and the corresponding angle of a second triangle corresponding angle of a second triangle have equal measures. In other words, have equal measures. In other words, they have the same degree of angle. Then the triangles are similar. Okay, that's test number 1. If two angles in two triangles that correspond have equal measure, they are similar. The triangles are similar. If the angles of one triangle, not just a particular angle. Okay, test 2 says that if the measures of the sides of two triangles, if the measures, the sides of two triangles form equal ratios in other words, proportions, then the triangles are similar. I have a graphic image here that I've cut and pasted in that I think is going to be a lot better than me trying to draw this myself. Here we have two triangles, and we have triangle. This is the symbol for triangle, this little triangle right here. Okay, we have triangles, a triangle ABC, and then we have triangle DEF. Okay, the order of the letters is important, so that angle A corresponds to angle D, angle B corresponds to angle E, and angle C corresponds to angle F. The order is important. Corresponding angles are basically what I just read off. Okay, this is the symbol for angle, so angle A and angle D are corresponding. Angle B and angle E are corresponding. Now, why are these corresponding? Because angle A and angle D have the same measure, 56 degrees. Why are angle B and angle E? Because angle B's measure is 83 and angle E's measure is 83. Therefore, they are corresponding angles. And then we have angle C and angle F. Both of those are 41 degrees. Now over here we have something a little bit different, okay? Corresponding sides. Now remember, corresponding sides aren't equal, the ratios of sides are equal, okay? So let's look at this. The side AB, and that's denoted by this bar across the top, okay, the side of AB and DE equals AB over DE, and AB is 2, DE is 4, so that equals 1/2. Let's go back again. Side BC and side EF. Okay, the ratio of those two sides is BC over EF, which is equal to BC is 2.5 and EF is 5, and that again equals 1/2. The last set of sides is AC and DF. And AC is 3. So we'll go AC over DF. So AC is 3, DF is 6. And that's again 1/2. So these two triangles are indeed similar, and these are the relationships that prove it. Now, up here, we had triangle ABC and triangle DEF. To say mathematically that they are similar, we have a sign that looks like this. Okay? It's a little squiggly sign. Then that means that triangle ABC is similar to DEF. Okay? So this guy means is similar to. Another way to show similarity is like so. We have A, B, C, and we have D, E, F. So what we're going to do is show you angles. So here, angle A and angle D are corresponding angles. That's indicated by these red marks here. Angle B and angle E are corresponding, so we mark that with 2 angles, or 2 lines, 2 arcs. And then angle C and angle F are also, and we mark those with 3. So those are visual indicators of which angles are corresponding angles in each triangle. Over here, let's do example 2, which this graphic here is a part of. So this is going to be example 2. It's on page 561. And it says, determine whether the pair of triangles is similar. All right, and then it says justify your answer, which means you have to prove what you say. You can't just go, yep, they're similar, next. One of the things that you need to remember about triangles in general is that the sum of the measures, okay, the sum of the measures of the angles in the triangle is equal to what? Yep, 180 degrees. That's a piece of information that you should have in your toolbox right now, being in algebra. If that's the case, we need to know what the measure of angle P is. Now, we don't know yet if these are similar. If they were, angle P would probably be just what angle M is. But we don't know that yet. We have to prove it. So we can't make the assumption that angle P and angle M are equal. We have to say, well, angle P for that triangle, what's the measure of that angle? How do we know this? Well, angle P, all right, the measure, and a little m in front of the angle P means the measure of angle P, all right, is going to be 180 degrees minus 51 plus 51. Both of these are little degrees, all right? Or it's going to be 78 degrees. That's angle P. So in triangle now, in triangle M, N, and O, angle N and angle O have the same measure. How do we know this? By looking at the diagram and seeing the two angles have a single red arc. That means that they are the same measure. So if that's the case, and remember again, we still haven't proven that these are similar, so we can't assume that N and O are going to be what R and Q are. So here we say we're going to let X equal the measure of angle N as well as the measure of angle O. Okay, then that means that the measure of angle N plus the measure of angle O plus 78 degrees has to equal 180 degrees. Just like a regular equation, we add the two x's together and we get 2x plus 78 degrees is equal to 180 degrees. We subtract 78 from both sides. Okay, this goes to 0, and we're left with 2x is equal to 102 degrees. Therefore, and the little 3 dots means therefore, x is equal to 51 degrees. So that means that since they're equal to 51 degrees, angle N and angle O are 51 degrees. So therefore you can say that triangle MNO is similar to triangle. Now here is where you need to pay attention to the order that you run this triangle through. M needs to correspond to angle P. N needs to correspond to what? Q, that's right. And O needs to correspond to angle R. And that is the answer to the question. And the justification for it is that N and O have the same measures as R and Q, and therefore M and P have the same measures. And if the measures of the angles of one triangle are the same as a second one, then the two triangles are similar by the test that we went through and defined on the last slide. Let's go through now and work on example 3. And that's going to be on page 561. Okay, and example 3 says find the missing measures for each pair of similar triangles. So that's in the diagram right here. And so we look at this and we say, what is it that's missing? What's missing is we have a measure and a side, two sides in both of these that are not filled in. So it says here, remember now, it said that these are similar triangles. Okay, so this, since the corresponding angles have equal measures, all right, then triangle TUV is going to be similar to triangle. And we look at this. Now here it's easy. The first two angles are in order, so we can just run around the triangle in the same direction. W, X, Y. If these triangles were rotated one to the other, this would become a little bit more difficult to figure out. Let's figure out what A is, what side A is. Okay, so we have WX over TU. And that's going to be equal to XY over UV. So remember now, WX and XY are all from the same triangle. TU and UV are all from the same triangle. Corresponding sides have to be, the ratios have to be equal to each other. So now let's go plug in the values we have for this. WX happens to be A, and TU happens to be 3, and that's equal to XY, which is 16, over UV, which is 4. We do some cross multiplication, okay, just like this, and it becomes over here 4A is equal to 3 times 16, which is 48. We divide both sides by 4, okay, and that becomes A. This goes to 1. A becomes 48 over 4, which is equal to 12. Well, that's A. What about B? Well, B, we do the same process, okay? WY over TV is equal to XY over UV. All right, let's plug in the values then. And that gives us B over 6 is equal to 16 over 4. Again, we do some cross multiplication. So that comes out to be 4B is equal to 96. We divide both sides by 4. This goes to 1. And we end up with B is equal to 24. Okay, so the missing measures of the sides are 12 and 24. All right. Okay, let's do part B of example 2. And that says you have this diagram here on the right-hand side. Now this is a typical type of diagram that you're going to see where you have two triangles nested inside each other, or one inside the other. And it says, it gives us this piece of information. It says that AB ABE, triangle ABE, is going to be similar to triangle ACD. All right. And we look here, and CD is something that we don't know. And AC, the whole length there, is something we don't know. So we need to discover what those two quantities are, what those two measures are. So these are already similar triangles, which means that the sides are similar. The ratios of the sides are proportional. If we look at this, BE over CD is going to be equal to AE over AD. Okay, because the corresponding sides of similar triangles are proportional. Let's drop in some values into this. BE is 10 and CD is X. And that's going to be equal to AE is 6, AD is 9. So therefore we have, cross multiplying, we have 6x is equal to 90, x is equal to 15. That's good, but how are we going to figure out y? Well, here's a way that you can do it, and this is where algebra really brings in other pieces of your math that you've learned. Remember Pythagorean theorem? That says that c squared is equal to a squared plus b squared. All right? Well, what are we trying to find? Y, that length y, AC, and that happens to be the hypotenuse of a right triangle, whose second leg we just found to be x. What if we did this? Y squared is equal to a squared, we'll let that be 9 squared, plus b, which is the x that we just found, 15 squared. Okay, this becomes y squared is equal to 81 plus 225. Then over here we have y squared is equal to 306. We take the square root of both sides. The square root of y squared is equal to the square root of 306. Therefore, y is equal to the square root of 306, or roughly 17.49 meters. These are the two missing measures that we needed to solve. All right, let's do the last example here. And I put both the drawing and the problem itself into our document so that it would be easier to solve. Back here again, it says Janelle is standing near the Washington Monument in Washington, D.C. The shadow of the monument is 151.5 feet, and Janelle's shadow is 1.5 feet. If Janelle is 5.5 feet tall, how tall is the monument? Well, obviously, the monument is not drawn to scale. So these shadows and these triangles form similar triangles, okay? So we need to write a proportion that involves x. We're going to let x there be the height of the monument. Okay, so we'll let x equal the height of the monument. All right, and so we just set our equation up, okay? Let's let Janelle's shadow, over the monument shadow equal Janelle's height. Oh, I spelled her name wrong, sorry. Janelle's height over the monument height. When you put it into words like this, it's not so terrifying. So Janelle's shadow from our problem is what? It's 1.5. What's the monument shadow's length? That's 151.5. And that would be equal to Janelle's height, which is 5.5 feet over the monument height, which is x, which is what we're trying to find. Okay, some fast cross multiplication. You have 1.5x is equal to 833.25. Divide both sides by 1.5. This goes to 1, and we have x is equal to 555.5 feet. Not so scary, right? Thank you for watching, and if you would like the video, that would be great. You can't comment on it because you guys are restricted, so if you would, either send me an email or comment in the link that's in the Google assignment. Thank you very much, and I will see you next time.